Thank you for that introduction. Um, like was mentioned in that little blurb just now, we're going to be focusing on the baseband processes of Doppler radar for this talk. And for an outline of my presentation, we'll go on a brief introduction on the types of scenarios we're talking about, the types of basebands, coupling, and consideration you have to give there, followed by the closed form approximation of our new architecture that we're proposing here, and then gain dependence and AC coupling experiments and validation. So for a brief overview of radar, like was said in the last talk, radar has been long considered for Bose extraction. Multiple types of radars have been, ranging from Doppler to FMCW to FSK. In this case, we are focusing on the Doppler baseband type of radar because of its sensitivity to the base micromotions with the least coupling due to modifications. In this case, with a simple circuit, the motions on the micrometer scale can be extracted while still allowing us to have the full wide range of application. In this baseband architecture, we have to be coupled into our RF portion due to the need for maximum application and dynamic range. When talking about this baseband coupling, there are multiple ways that people have gone about solving these issues. In the left, you'll see a DC coupled system. And the point of this DC coupled system is to retain the DC information from the Doppler section that is a function of the range of the target and its wavelength to the radar, while still retaining the high dynamic range that is sought after for these low frequency motions. The drawback in that kind of architecture is the increase in complexity and price and compared to more simplistic or more less complex architectures. In most cases, people use AC coupled, which is in the middle. The only problem with an AC coupled system is that in this AC coupled system, this capacitor here can cause a high amount of distortion due to the charge time being controlled by this series fed resistor needing for Biosine based processes to be a large capacitor. To address this issue, we've proposed adding in this fast start circuit denoted by this diode, which allows us to have the same simplicity in circuit layout and components as a regular AC coupled circuit, while allowing for a wider range of capacitor values to lower the cutoff frequency and lower the start time from the order of minutes in the case of a microfarad and megaohm resistance system to the order of seconds. Looking at just the AC architecture, what you can see from the cutoff frequency is that it's controlled by this RC that is controlled by the series resistance capacitance on the system itself. And this RC time constant causes a charge time to be induced in the circuit, which can be noted as the figure on the right, which shows as we change our gain and change our capacitance, the charge time lengthens and shortens relative to these factors that you would want to maximize. The startup time for this type of systems in the Biosine case, as I mentioned before, is usually on the order of minutes due to the capacitance needed to couple into the circuit for Biosines to have a cutoff frequency of 0.1 hertz. In the case of our system, we've done some closed form approximations on the circuitry, which allowed us to extract these two equations you see down here. This first equation, this error, is a function of the manufacturing error in op amps and this offset voltage causing a saturation and a limit on the max total gain we can get out of the system. While this bottom equation is the closed form approximation of the time domain with the diode as well as the rest circuits of a conventional AC coupled system. Looking more into this offset voltage, as I mentioned earlier, the maximum voltage is contained that you can amplify to is contained between your bias and your offset, with a larger, this being that if you get unlucky with this offset voltage, if it's on the order of hundreds of millivolts, you lose your overall amplification of the system, where before maybe you could amplify up to 200 times in the near scale and not have any saturation or any issues. If this offset is relatively large enough, you can only amplify up to maybe 100 or 150. Looking at our gain dependence, as shown in those previous equations, we have this startup time, which is a function of our effective resistance due to the capacitor, resistor, and diode in the circuit, as well as the voltage and gain of our full system. And as you can see from this equation, that as we increase the desired gain that we want, this startup time that we are expecting out of the circuit through both simulation and our closed form shows an increasing delay in the actual time for startup, or time when we leave saturation of the circuit. The factors that control that is the diode forward voltage, which makes the selectivity of the diode very important for both its parasitics and its charge sign. Since due to the way that the capacitor is charged with the diode, there is an exponential charge time that has a section towards the end of the tail that the diode turns off, where the capacitor is left with its own native charging from the series resistance. And this causes so therefore the forward voltage that we want to be as low as possible so that we don't have a long time for this charge time from the native huge impedances. When comparing this to actual real values, on this left side you'll see an experiment carried out with a baseband that's just AC coupled with a signal generator, where we feed in a superimposed biosign signal shown by this wavelength being amplified at 3 different AC levels. And as you can see, when we compare it against the derived times from our closed form to the real times, you can see a clear relationship between the gain that you want to the charge time, where the higher the gain, you can expect your charge time to approach larger and larger numbers. Looking at the same circuit, but in the frequency domain, you can find that the baseband performance is still a high-pass filter, where the impedance is now controlled mainly by this parallel diode to the system, causing this R effective to cause a modification on our transient response, where the circuit without the diode has this desired low frequency cutoff of about 0.1 and below hertz. But after adding in the diode, our frequency is shifted all the way up to about 11 millihertz, and our phase is again increased along with that. The shift in results of this can be seen from a real-life experiment with an actuator using a 120 gigahertz Doppler radar, where on the left you'll see the idealized case, where it's just the actuator with AC coupled system without the fast startup that has been allowed to charge for about 2 minutes. And on the right you will see the circuit with the startup that is charged in about 20 seconds, but because of the diode has caused some slight variations in the base constellation. So in conclusion, what we present here is an analysis of a new fast startup circuit that builds off of simplicity and speed without adding in price and overdue complexity, as well as 2 closed form models to allow for fast simulation and characterization of the system. And in the future, we'll be working on developing the amplifier model due to some irregularities that we saw in the offset voltage and accounting for more parasitics in the system. Here's my contact information. Any questions, I'd be happy to answer.